In this video, we will talk about the concept of mass and also about Newton's second law. First, mass. Mass is a very difficult quantity to define, but right now we will think of it in terms of its ability to resist acceleration. Imagine somebody throw at you a golf ball at 10 meters per second. Well, let's say 2 meters per second. We don't want to kill anybody. 2 meters per second, and then they shoot a bowling ball at 2 meters per second. Which one do you think is going to be easier for you to stop? And of course, it's going to be the golf ball because it has less mass, so less inertia. So there is a relationship between mass and inertia, and this is one way to define mass with respect to its inertia. It's the property of an object that specifies how much resistance it shows to change its velocity. So for a constant force, if force is constant, right? If you have a small mass, you're going to have a huge acceleration. If you have a big mass, you're going to have a small acceleration, which means the relationship between mass and acceleration is inversely proportional. Now, with constant mass, we're only dealing with, let's say, the golf ball. If you have a small force, you're going to have a small acceleration. But if you have a large force, you're going to have a large acceleration. That means the force is directly proportional to acceleration. These observations were summarized by Newton into an equation that says, well, the acceleration is going to be, the acceleration is going to be proportional to the force and inversely proportional to the mass. And then what Newton gave us was this equation that the total force external acting on an object is going to be equal to its mass times its acceleration. The acceleration is a vector, force is a vector, and this is Newton's second law. So let's take a closer look. You need sigma. Let's discuss each part of this equation. The sigma, well, this symbol is Greek letter sigma, uppercase, and it means sum. Then this is the external force. External force is you add all the forces that are external to an object, and that's going to be equal to the acceleration of that object. Ma is not a force. The net force, which comes from adding all these vectors, can be related to the acceleration of whatever mass. External, look, if you sit on a table, no, sorry, not on a table. If you sit on a chair, but that chair has wheels, and then you push on the chair, you're not going to go anywhere because the force with which you're pushing on the chair is part of the system. That is an internal force and cannot be put on this equation. If you have motion in one dimension, well, then just one equation. But if you have 2 dimensions or 3 dimensions, then you're going to need the version of the equation for each one of the axes. Sum of forces in x, sum of forces in y, sum of forces in z. And that's going to give you the acceleration in x, in y, or in z of your object. Before we do a little problem, let's just remember one thing. if force, the units of force will be the units of mass times acceleration, then mass is kilograms and acceleration is meters per square second. So the units of force will be kilogram meter per square second, right? And this we call 1 Newton. This is the international system. In the British system, we use the pound, okay? Now, one difference between pounds and newtons is, let's say somebody has a mass of 100 kilograms. Well, then the weight will be 100 times gravity, 9.8, is going to be 980 newtons in the international system. In the British system, 100 pounds is the mass and 100 pounds is the weight, which makes no sense. In reality, the unit for mass in the British system is the slug, but nobody uses it. Now, another difference is if I'm on Earth, I have 100 kilograms of mass, 980 newtons of weight. If I go to Mars, I still have 100 kilograms of mass, but a different weight because gravity is different. If you do this, if you try to do this in the British system, good luck. I'm not even going to go there. Now let's try this little example. We have a puck of 3.3 kilograms sliding on frictionless horizontal ice. Now it's struck twice by two hockey sticks simultaneously. So if I draw my puck, we'll see that one is hit by a force of 5 newtons at 20 degrees, and the other one is hit by a force of 8 newtons at 60 degrees. The question is, what's the acceleration? We only have one equation so far, so we have to find the net force, external, and that is mass times acceleration. So to find the acceleration, we have to divide the net force over the mass. So let's find the net force, which of course we know is force 1 plus force 2. Force 1 plus force 2 over the mass. But force 1 can be decomposed like this and like this. Force 2, same thing. So force 1, we can say, yes, it's 5 newtons at negative 20 degrees with respect to the x-axis. So that's the same as saying 5 cosine of 20i minus 5 sine of 20j. Negative, because you see it's going in the y-axis. Same time, F2 is 8 newtons at 60 degrees, or 8 cosine of 60 plus 8 sine of 60j. Now we need to add the forces, so we add these two, sum of forces, external, and it's going to be this plus this minus the 5 sine of 20. So when you add 5 cosine of 20 plus 8 cosine of 60, we get 8.7 in the I direction. And then when we do 8 sine of 60 minus 5 sine of 20, we're going to get 5.2j. To get the acceleration, what we do is, well, this 8.7i plus 5.2j divided over the mass, divided over 0.3 kilograms. This was in newtons. So the answer final is 29i plus 17j meters per square second. We can use, so this looks like 29 and 17. If you use Pythagoras, you're going to get an angle of 31 here and a resultant of 34 meters per square second. So that will be the answer. 30 34 meters per square second at an angle of 31 degrees, which I can leave like this because it's expressed with respect to the positive x-axis, or 0 degrees.